Hello and welcome to the GC online webinar. My name is Dr. Mazot. With the advancement and penetration of the digital tools in dentistry and in orthodontics, the orthodontic profession is going an impressive conceptual change. The use of scanners, 3D software and printers provide us the orthodontist excellent tool to analyze, demonstrate, plan and perform the orthodontic treatment better, faster and more secure. In the following webinar, we will discuss those tools to appreciate their contribution to the orthodontic everyday work. The industrial manufacturing of brackets and wires has an important influence on the orthodontic treatment progress and result. There are three common techniques in bracket manufacturing: MIM, metal injection molding, and CNC, computerized numerical cutting, which is a development of the old milling technique. The third manufacturing technique is a combination of the MIM and CNC, in which the bracket body is MIM and the slot is later cut by the CNC procedure. GC brackets are made in such combination technique, providing a high precision bracket with a fair price. Together with brackets, the wires are extremely important by their physical and surface properties to provide the optimal force and resistance, which are essential for the treatment progress and for the prescription manifestation. Accuracy, performance provide the clinician the best required control for teeth movement and influence directly the results. In the following figures, the MIM process is demonstrated to clarify the manufacturing technique. Initially, a powder containing metal and some other materials are inserted into heating chambers and heated to the fluid status. Then under high pressure, the metal is injected into cavities to gain the bracket shape. The next two steps, the debinding and the sintering, are meant to extract the unrequired materials and to maximize the condensation of the raw bracket. On these two last steps, a substantial shrinkage is expected. The last step is cleaning and smoothing. The accuracy of the bracket is highly dependent on the sensitive procedures and the quality of the metal powder. The cavities has also a limited working lifetime. The CNC, computer numerical control cutting, it's a different procedure in which the brackets are cut out of a raw material. The process is slower than the MIM, but with higher accuracy and quality of the brackets. The use of proven high-quality products is important to ensure the bracket and wire quality. On the other hand, the doctor's skills and experience are the most important factor to influence the treatment for all points of view: the control, the progress, time and outcome. And of course there are some objective limitations. Those limitations will manifest in the time of the treatment progress, the working stage, and later at the end of the detailing stage, which are the two stages that might require substantial treatment time and can influence the treatment outcome. Dr. Andrews, the father of the straight wire technique, presented his concept of straight wire appliance based on 5 studies. Dr. Andrews has acknowledged the difficulties to fully control the biomechanics and the side effects of the teeth movements. In that spirit, he has developed a series of brackets with different torque and angulation according to the different clinical situations in order to compensate for the expected undesired teeth movement. His approach was later the foundation for most existing prescriptions today. The understanding of the reason for the difficulty to control the teeth movement is essential. Those reasons can be divided into 2 categories: doctor's limitation and technological objective limitations. The first category, doctor's limitations, we can mention the following: bonding errors. All orthodontics suffer from bonding errors. Visibility, age, tiredness, patient, tooth morphology, and more can be a direct reason. the inability to calculate accurately the required overcoming compensation for the expected desired teeth movements. The technique adopted by the doctor. The doctor must be well familiar with the used technique. Some techniques are known to be more favorable for achieving easier and better treatment outcome. The GET prescription is one of the best existing techniques today, based off a unique 0.20 by 0.28 slot size and high-tech wires. The importance of manufacturing was discussed previously to illustrate the importance of accuracy and quality. In Fig 1 to 4, we can evidence the differences in bracket accuracy and the surface quality of the brackets and wires. The European regulations has acknowledged the manufacturing limitations, allowing an acceptable deviation from the original required dimensions. One of the most interesting factors is the fact that the brackets are not individualized. They are designed for the average tooth morphology. They do not consider morphological deviations such as accentuating curvatures, small or peg-shaped laterals, and other exceptions which are common and eventually will influence the end teeth position. From the above factors, the bracket system and techniques and the accuracy of the products will be manifested as increasing play and loss of tooth control. Play is considered to be a major player in the control of the teeth movement, the expression of the system prescription, treatment time and outcome. It will be manifested in uncontrolled or undesired teeth movement, such as tipping, rotation, and torque loss. Good knowledge and special efforts are required from the doctor in order to overcome and control those side effects. Theoretically calculating the play of a 0.19 by 0.25 stainless steel wire in a 22 slot is considered to be about 9.5 degrees, leading to an actual torque of only 7.5 degrees in the MBT prescription for the upper center incisors and 2.5 degrees for the rod prescription. Amazing findings were found in the research presented in this slide from 2015. The play in a 0.22 slot bracket, tested with a 1925 SS wire, was varying up to 36 degrees in poor quality of brackets. Passive brackets were found to be less effective to control the torque due to the oversized slot and the lack of active force to seat the wire inside the slot. Using a bidimensional approach of 0.20 and 0.28 slot with active self-ligating bracket can allow better results. And not only the torque is influenced. In general, accuracy, slot size, and ligation altogether are important factors influencing the seat of the wire in the slot, controlling the tooth position and the treatment progress and outcome. Different brackets have different physical dimensions, such as the width and the slot height from the tooth surface, which will have a direct impact on the degree of the undesired teeth movements. In the following slide, we can see 4 types of ligations. Each one of them will express differently the control of the tooth movement and position. The ligature wire, Fig number 7, can seat the wire best in the bracket slot, pushing it completely all the way in contact with the lingual wall of the slot, fully correcting the tooth position. But since a higher friction can be developed if the same ligation is used in all brackets, the overall developed friction level can be creating a binding, stopping or slowing down very much the teeth movements. In case of a 1 mm lingual teeth position, a 0.14 wire in a passive self-ligating bracket at Fig number 5 not only will not be able to fully correct the malposition, but also will develop a higher friction than the elastic module or the active self-ligating bracket. The active self-ligating bracket has a spring clip as a locking mechanism. This spring is located inside the slot lumen at an estimated 60% height of the slot, figure number 6, allowing better control with less friction than the passive self-ligating bracket. The spring quality, of course, is crucial for the active self-ligating proper function. The incisor or occlusal and gingival walls of the slot are responsible for the vertical position control and on the degree of the tipping. The bracket mesiodistal axial slot width will have an impact on the degree of the tipping and the rotation control. A 0.22 slot will require a bigger size of wire to control the vertical and the tip control of the teeth. A 0.20 slot will also provide better and faster torque, tip and vertical control. It is estimated that about 20 to 30% of the whole treatment time is wasted to overcome the added inaccuracies during the treatment. So how can the latest technological, digital hardware and software assist us to better and faster achieve our treatment goals? The evolution and improvement of the 3D scanner software printers changed and improved our attitude to the orthodontic profession. The indirect bonding is a result of these 3D tools, allowing the orthodontics to beneficiate improved accuracy, smart individualization, better control, leading to the faster treatment, increased safety, and better outcome. In the next slide, we will discover more about those tools and the benefits they can provide us. 3D scanners are made to create the 3D model, which later can be processed in the 3D software. The 3D scanner is using a set of digital high-definition cameras to build a 3D model. The first generation were the table or the lab scanner, in which the casted model were scanned. At a later stage of the table scanners, the impression could be scanned directly and no casted models were required. The scanning of an impression was not so forthcoming due to the undercuts which were not seen by the scanners. The intraoral scanners were developed later. The intraoral scanners were developed later in order to replace the impression taking. A good intraoral scanner system depends on two components: the hardware, the handle and the cameras, and the processing software. The intraoral scanners had gone through important developments and today they can offer many advantages over the conventional impressions. Still, the high cost of the intraoral scanner system is high and not affordable to every dental office and clinic. The intraoral scanner is made of a set of optical digital cameras and reflectors. The scanning is done by taking multiple shots, frames, as single images or as a video, which later are processed by image processing software to create a 3D object. The following features are important for a good intraoral scanner. Field depth, the capability of the lens to adapt very fast to a changing distance from the scanned object by auto-zooming and focusing. The bigger is the field depth, the better it is, allowing the operator the freedom to move over the teeth without the obligation to keep a constant distance. In some scanners, the auto-zooming and focusing of the lens is done by a laser beam reflecting from the teeth. Interferences. While scanning, the soft tissues such as the cheeks, the operator fingers, tongue can be captured in the scanning field. The gingiva, saliva, and blood are some other interferences, which the scanner needs to overcome and the software to be able to differentiate. In the past, there was a need to place a powder over the scanned area to dry the field and avoid reflections. Today it is not required anymore. The auto-calibration. It's another important function, which is required to allow a constant scan from scan to scan without any distortions. Stop-start function. It is important, extremely important feature of the software. The possibility to stop at some point and restart again from the same point or from another point allows maximum flexibility for the operator. Those mentioned important functions are essential for the fast and accurate scan, with the minimal 5 size required, and finally, the minimum time requirement of learning curve. The final result is the STL file. The scan result is an STL file. This digital file is later processed in designated 3D software for different procedures, including orthodontics. The STL file is preferred to be an open file, in order to be used with any software and does not require any conversion process, which might be a source for inaccuracies. Unfortunately, still there are some companies who limit their appliances for a certain software only, or obligate the orthodontics to use a specific appliance in order to use their products. The orthodontic 3D software uploads the 3D scan to create the 3D model of the patient. From this point, a door for a new world is opened. The orthodontist can easily obtain impressive amount of information that can be used for different purposes such as viewing, demonstrating, analyzing, in order to plan the best treatment option for the patient. The 3D model can also be exported for different users and easily be viewed by any 3D simple viewer. In order to extend the use of the models for more advanced features, the models need to be segmented. The differentiation of and definition of each tooth from the gingiva. At this point, some information such as bolt-on analysis is obtained automatically. Many parameters, such as the overjet, overbite, arch length discrepancy, and other, like crosscuts views, can be obtained from these 3D models. A very important feature of the 3D software is the possibility to identify the bony borders of the treated arches, increasing the treatment safety. In some 3D software, a CBCT scan can be imported in the software, allowing to identify the current root position and thickness of the bone and to assist the teeth movement according to the anatomical bone borders. In this way, the operator can choose the correct wire parameter or shape in relation to the correct required teeth position in the bone. Here we can see a sample of a calculation easily done in order to relate the teeth's current position in relation to the bone, calculate the lateral required teeth movement, expansion of the lower arch, and accordingly calculate the upper teeth position. And of course choose the correct wire size perimeter accordingly. Bracket positioning is one of the most important advantages of the 3D software. At this step, the brackets are accurately positioned and smart calculations are done, and the final result can be also seen to demonstrate the final occlusion. The bracket positioning is done automatically by the software itself according to the operated preferences, type of brackets, specific prescriptions, Roth or MBT. Later, the operator can verify and adjust if required. The bracket positioning can be viewed from different perspectives. It is numerical controlled to allow the maximum accuracy even for the posterior teeth. The most important and the heart of the bracket positioning is the accurate smart positioning. At this stage, some specific calculations are done in relation to the specific case, treatment plan, the biomechanics, and the expected side effects of the teeth movements according to the bracket chosen for the respective case. Those calculations are then accurately applied to have the bracket digital setup. The main objective is to allow the shortest, easiest, and the fastest teeth movement to their final best position, and without decreasing the working and the finishing stages time, and by that, to increase the safety of the treatment in the shorter treatment time. An example for the smart calculation, it is presented in the next slide. In upper extraction case, the bracket position can be adjusted in order to compensate for the expected side effects, such as rotations, tipping, and control the torque loss in the respective bracket system and the wire size to allow the optimal tooth movement and best final position and result. It is important to accentuate that those calculations will be different from different type of brackets according to the physical dimensions. The indirect bonding tray is the tool to transfer the digital work done in vivo, intraoral. Indirect bonding trays exist in orthodontics for many years, and their advantages are known to save chair time, increase accuracy, even when used by other personnel such as the assistants. The disadvantages are also known, such as the inability to remove the excess of the bonding material before setting. There are several types of indirect bonding trays. The first generation used the brackets positioning done on the plaster model, over which a double vacuum foil, a soft one and a hard one were used as seen as in Fig 9, or a soft silicone was used as the first layer, over which a hard vacuum foil was used as seen as Figure 10. With the increasing use of 3D printers, brackets are initially placed on model using different methods: printed models with leads, printed models with the brackets, printed keys, to allow the bracket to be positioned incorporating the accurate smart bracket positioning previously done using the 3D software. Fig 11 presents a printed model with brackets on it, over which a flexible vacuum foil is used to create the indirect bonding tray, with indentations in which the brackets are later inserted in. Fig 12 is a printed key, which is placed on the model as guide for the brackets to be positioned. After brackets are being positioned, the key is removed and the vacuum foil technique, as described before, is used over the brackets to create the indirect bonding tray. With the development of clear flexible resins, the 3D printed indirect bonding tray is printed and the brackets are placed in the indentations. This tray allows some degree of exposure of the brackets and allows partial control of the excess of the bonding material. An interesting feature is the 3D printed edge tray, which presents a combination of safety and clinical advantage. The etching material is injected in accurate windows, base size and shape of the brackets in order to avoid unnecessary enamel edge surface, which exposes the enamel to discoloration and increase the risk for caries. In addition, it facilitates removal of excess of bonding material, which was not removed earlier. 3D printers were at first introduced in dental profession in dental laboratories due to their high cost. Today, with the development of different 3D printing technology, the printers became more and more used in dental offices. The use in the orthodontic office offers many advantages for the orthodontist. The first technology of 3D printers used injected melted resin. The resin is heated and then injected through a moving nozzle over the printing platform. The accuracy and smoothness can be at high level due to the uniform dispersion of the resin. The disadvantage of this technology was that only one type of resin could be used. When different resin materials needed to be used, the change of the resin required a complex procedure of cleaning the system and waste of resin material. In the new printers, more than one material can be used. Still, the high cost of these high-quality printers makes them not applicable for all dental offices or clinics. Later, a second 3D printing technology was developed, a technology using light source to cure a light-sensitive resin. The resin is placed in a resin bath and a printing platform is used to cure the object on. The platform is slowly moving up as the material is light cured in layers. There are two different light curing technologies, DLP and SLA. SLA, stereolithography. It is one of the oldest forms of 3D printing, dating back to the early 80s. The laser sits below the bath with the resin. The beam point deflects off from a rapid moving mirror that directs the beam to the appropriate point upward into the resin. By swifting the laser across the bath of resin, a layer of the print is drawn, according to the design specifications, layer by layer, on an upward moving platform. The accuracy is good due to the small point laser curing, but the process is very slow. DLP, Digital Light Processing, as a 3D printing technology, has its roots in an image projection technique born in the late 80s at Texas Instruments. DLP projects each layer, creating an illuminated plan where photopolymerization will occur. It is not restricted to a single spot, as the SLA. Instead, the whole layer is formed at once. Here, a set of digital micromirrors device, DMD, which is located, sits between the UV-emitted lamp and the resin, are responsible to control the lamp light to allow the polymerization of the resin according to the digital design. Modern DLP projectors typically have thousands of micrometer-size LEDs as light source. The on and off states are individually controlled and allow for increased resolution. Some DLP printers replace the DMD with an LCD screen, which provide higher accuracy with noticeable impact on the price. Using digital 3D tools such as scanner software 3D printers, which will provide us improved accuracy, better control in combination with the other advanced smart technologies, will provide the best option for easier and faster treatments with a higher safety and better outcome. Self-ligating brackets were introduced about 90 years ago in the market and developed through a modern smart tool such as the GET system, which combines a unique bidimensional approach of 020 by 028 slot with high manufacture precision and high-tech wires. Self-ligating brackets can be an excellent tool when the user understands the specific characteristics of the different types of self-ligating brackets, their specific biomechanical and clinical behavior, and chooses and uses correctly the optimal system with adequate philosophy. Understanding the self-ligating bracket systems offer us the advantage of efficient and control. The self-ligating bracket systems, due to the fact that they do not use elastic modules, present very low friction system. As low friction system, they can be considered as determinant systems, that forces can be calculated and as a result, additional forces can be applied with good feasibility. The self-ligating bracket systems, due to the fact that they do not use elastic modules, present very low friction system. As low friction system, they can be considered as determinant systems, that forces can be calculated and as a result, additional forces can be applied with good feasibility. In addition to the fact that self-ligating bracket systems present much less friction and higher play and are the basic characteristic of self-ligating brackets, which provide us the realization of those initial three steps together. And together with the use of the GET system, a bidimensional system, 020 by 028 slot, as a self-ligating system offers improved biomechanic behavior, which facilitates even more the treatment results. GET is an active self-ligating bracket, which provides better sit of the Y in the bracket slot. The 020 slot, which provides better rotational and torque control with excellent sliding and less side effects of the tipping. The combination of new high-tech wires provide the possibility to incorporate rectangular, bigger size wires to exercise multiple steps with light forces with minimal discomfort to the patient. In addition to the fact that cephalogating bracket systems present much less friction and higher play and are the basic characteristic of cephalogating brackets, which provide us the realization of those initial three steps together. And together with the use of the GET system, a bidimensional system, 020 by 028 slot, as a cephalogating system offers improved biomechanic behavior, which facilitates even more the treatment results. GET is an active cephalogating bracket, which provides better sit of the wire in the bracket slot. The 020 slot, which provides better rotational and torque control with excellent sliding and less side effects of the tipping. The combination of new high-tech wires provide the possibility to incorporate rectangular, bigger size wires to exercise multiple steps with light forces with minimal discomfort to the patient. The new high-tech wires present excellent physical properties and accuracy. The bioactive wire is a biological thermal activated wire. Presents three areas of force, according to the group of teeth. Smallest force on anterior teeth, presenting the smallest root surface. Moderate on the canine premolar area teeth, and the highest at the molar area. The BioEdge is a thermal activated wire with constant low force. The BioEdge is offered with forces ranging from 100 to 300 grams, dispersed uniformly along the wire. Both the BioEdge and the bioactive wires exhibit high-range constant force, which makes them an excellent choice as the first wire to allow the multiple functions and the achievement of the multiple steps together. The GET cephalogating bracket system wire sequence is presented in the following slide in the green zone. The first wire being 020 by 020 bioactive or bioactive light, followed by the 020 by 025 bioactive. Those two wires help to finish the leveling alignment, start the control of torque, start closing spaces, and allows the controlled inter-arch elastics. The third wire, being the 019 by 025 stainless steel, help to achieve the treatment goals, finalize the torque and the stabilization stage. 016 or 018 stainless steel wires are used for the detailing and for the finishing. The blue zone reflects two clinical situations. In case of a severe crowding, can start with the 014 initialoy or 018 by 018 bioactive, followed by the 020 bioactive light, and then just follow the protocol in the green zone. A 020 by 025 stainless steel can be used in cases of need of arch control and stabilization. In those cases in which intermaxillary elastics are required, the possibility to use them with the bioactive or BioEdge wires in cephalogating system is possible thanks to the low friction in the cephalogating bracket and with the understanding and the smart use of the intermaxillary elastics. Intermaxillary elastics are defined by the diameter and thickness. On the plastic bag of the intermaxillary elastics, there are values of size and force, for example, quarter, high, or 4.5 ounces. Each ounce is approximately 28 grams. When stretching 3 times of its original diameter, the elastic will exercise the mentioned force. For example, a quarter medium elastic will exercise 99 grams of force when stretched from 6.4 to 19 millimeters. Choosing the correct size of elastics must be done knowing the distance between the 2 points of elastic application. The average distance between the upper canine and the lower first molar is about 20 to 21 millimeters, respectively matching the quarter-inch elastic. The BioEdge or the bioactive can withstand these forces without deformation, and the low friction in the active cephalogating bracket will allow a good sliding with good control, and with the 3D smart individualization leading to the optimal teeth movement. The combination of high-quality self-ligating brackets, innovative wires with the digital smile orthodontics, and the unique GET system can offer the orthodontist the best tools for faster and better results. I, Dr. Mazor, would like to thank you for joining this webinar. Hope to see you soon in our other webinars.